Okay, so this is the first project, flat die optimization. My group includes Molly Galvin, Caleb Grolman, Justin Limkaichong, and myself, Aaron Mackert. The main goal of this project was to study how die scale affects the performance of a hypothetical flat die. In class, we followed a CompuPlast tutorial making a die of around 2,000 millimeters in width and about 150 millimeters in length, which isn't really realistic in terms of the dimensions as far as real dies go, but it still worked as a teaching tool to show how to optimize a flat die to get under 5% variation in the volumetric flow rate of the melt exiting the die, which is the goal we're trying to achieve. So for this project, we scaled up that tutorial die and also scaled it down, doubling and halving respectively both the width of the die and the mass flow rate of the material. So in the next section, the next clip, we'll be showing how to do that in CompuPlast, and then we'll discuss the results afterwards.
So the first step is to open our CompuPlast and create a new file. For this one, we named it into project number 1. So what we did was follow the tutorial as stipulated. So opening the tutorial document, located in page 14, we locate the flat die tutorial. So the first thing that we will change would be the die flow domain width. So as stated, we will change it to 2,000 millimeters or 2 meters. We'll keep our number of divisions the same as 10. Then we'll go to the feeding channel. So the tutorial wants us to change our round channel to a square channel. We'll then change the height to 10, channel length to 100, channel radius to 4, and transition radius to 8. So the next important thing we will do is to add section number 3 and section number 5. So here, we'll now add section number 3. We'll rename it. Then we can also rename the section number 4 into relaxation chamber. So afterwards, we can now edit our manifold. So the first thing is to change it into a teardrop elongational flow. Then we will follow accordingly the values. So as said, we'll change 20 to 45. Then 15, go to 30. Subsequently, keep it at 20, 7, and finally 14. As noted, we can see the pink marks, which means that it was invalid. Thus, if we have went forward, that would have not worked. Afterwards, we'll now go to the restrictor, change it to gap constant. Initially put it at 50 and 10. Later on, we'll change this greatly or make this our main factor for variant. We'll also change the gap and set it to 1.050. Next step, we'll go to section number 3. We change it to 1.050. Again, 1.050. Noting that we set it at length constant, 3 and 3. We also changed the channel length from 1 to 10 millimeters. For the relaxation chamber, which is section number the 4th section, we'll change it and set it to gap constant again, similar to our restrictor. Put it at 10 to 20 millimeters. Then we again set the next one to 20. We again change the gap from 1 to 3 millimeters as stated in the tutorial. We now move on to section number 5. And as said in the tutorial, we'll keep the length constant, but change the values. So we set it from 1 millimeters to 3 millimeters and change our channel length to 1 to 10 millimeters. We also kept the GE constant to 1. Finally, we'll go to the lips and make a gap and length constant at the lips. So 1 and 15. Now we will save our geometry and go back to dye project. And just a quick run through that we did it correctly. Distributor with the 6 manifold dimensions, restrictor. Section number 3. Relaxation chamber. Section number 5. The lips. We'll close it and save. Now that we have set up our dimensions, we can now go to project data and start our analysis. So we will create new as done, and we will name it project 1 optimization and open it. So as seen, our dye project number 1 is now loaded automatically. And we'll now go towards the different initial settings that the tutorial wants us to do. So it is located at page 28. I will now zoom in and place it beside us for us to follow. So the project, we would want to scale up or scale down, and this will be reflected later on. So the first step would be to change our HDPE from 0.1 mi to typical HDPE 5 to a 5 mil flow index. We want to select past dye deformation and include lip shape optimization. Again, we now want to change our MFR to 500 as seen and change the material as said beforehand. Just ensuring that correctly changed. The next step, we went to the parameters, and the tutorial would want us to change our calculation error tolerance for a past dye calculation. So this basically improves our analysis. So we'll keep all the settings constant or the same, standard solver, approximative, and use left to right symmetry. Now for the temperature, we'll set our top temperatures plate to 200 and our lips to 150. And we will do the same thing on our bottom temperature, where we set our plate to 200 degrees Celsius and our lips to 150 degrees Celsius. Next, we will skip our lip profile optimization. As noted, we can actually change our max allowed gap change, but we will not do that. For past eye deformation, the tutorial wants to set deformation distance to 300 millimeters, heat transfer coefficient to 15, environmental temperature to 20 degrees, and our line speed to 6.2. Now just save the project and save all data. And just to solve and show our differences, this initial settings will give you 12.38% in flow variation.
Here we will take a look at the 1000 millimeter die, change the materials in the MFR from 500 to 250. We'll look at the parameters and the temperature, and the die project will probably change to 1000 millimeter for the width. So materials will change this from 500 to 250. Die project will change it from 2000 to 1000 millimeter. Number of divisions stays the same. Now we will take a look at trying to change the restrictors. Initially when we did it at 50 and 10, we got 52.9%. But when we change it from 50 to 25 and 13, pre-optimization, we got 1.708%. Now we look at the feeding channel, the channel length, and change it to 200. And now we get 1.492%. Now for post-optimization for lip profile optimization, we get 0.7247%.
Yeah,
All right, once we've completed that one, we go to the new die, which is going to be the 4000 millimeters wide. So that requires us to change the kilograms per hour from 500 up to 1000. After that, we change the flow width to be 4000 millimeters. And then we do the restrictor, leaving it at, changing it to 50 millimeters as the length, with 10 millimeters on the side. When we do that, the results end up being 56.75%, so it needs to be optimized. We now change the restrictor length to be 105 millimeters in the middle and 22 on the sides. We run that again, and now we're down to 6.09%, which is much better, but still needs a little bit more optimizing. Next thing we do is change the feeding channel length to be 80 millimeters. Brings it down to 5.829%. Still a little bit more optimization needed. So we optimize the lips profile. When we run that, we get this new profile. And with that new lip profile, we end up running it again to see how the overall graph turns out. Brings it down to 0.7635%, which is well under 5, so it's near perfect. And that's our project.
Okay, so this is the results and discussion section. This video, we're going to post the link in the document. We're going to upload the video to YouTube. We'll also attach the link to the email as well for convenience. There'll be a link here when you actually open the final document. So we showed what we did, and we're just going to look at what was effective and how it kind of worked. So for both dyes, we had pretty much the same process. We adjusted the restrictor first, and then the feeding channel, and then did the dye lip optimization. For the 1000 millimeter dye, these were the values that provided the best flow rate variation, as in the lowest. And as you can see, that was all we needed to do really in order to get it under 5%. The variation is very low. You wouldn't really need to make any adjustments after that, but we did anyway because we wanted to see how low we could get it. So as you can also see, if you increase the length in either the center or the edge, it increases the pressure drop because the melt has to travel a little bit further. It's just a minor observation. So the next thing we did was adjust the feeding channel length, and this didn't really have a substantial effect compared to before because it was already very well optimized. The optimal value we found was 200 millimeters, and the flow variation reduced by a very small amount, around 0.2 or 0.3%. So this would probably have a more substantial effect if we did this first without adjusting the restrictor. We could see what the feeding channel length does on its own. We increased it here for the 1000 millimeter one, but later on we see that for the 4000 millimeter dye, decreasing the feeding channel length actually helped, although it wasn't substantial in either case. So here we have our screenshots, just showing the dye lip optimization and the flow rate variation here, like the final results. So with the 4000 millimeter dye, same process as I said before. We found the ideal values for the edges and center of the restrictor, but this time the flow rate variation didn't drop to under 5% right away. The best we could get was 6.09% with these ideal values, and everything else was above that when we changed either the center or edges. So we once again tried to adjust the feeding channel. This time we found that reducing it helped more, but it still didn't bring it under 5%. It only lowered it by 0.3, 0.2% again. Not very significant. But when we got to the dye lip optimization, as shown here, it really improved it a lot. We have all the results in a table here. So it brought each of them down to below 1%, even though it was above 5% for the 4000 millimeter dye initially. So with these three steps, each one was well optimized in theory. But probably the most interesting thing to note is initially, before optimizing it, the 2000 millimeter dye from the tutorial, that one was around 12.38%. But if you scale it down or up, it's drastically higher, around the same actually for the 1000 millimeter dye and the 4000 millimeter. It's about a 4% difference between them, but that's a huge jump. So this allowed us to come up with a theory that there's kind of like a middle ground in terms of the width-length ratio, and how Compuplast calculates it. There's kind of like an ideal range for the melt to flow through and spread out. That was our theory anyway. So here's the values for each step, and it worked well for the first two dies. The first step, I mean, just adjusting the restrictor, that was good enough. But for the 4,000 millimeter, we needed to do the extra 2 steps to actually get it below 5. But after optimizing the die ellipse, it was well below 5. So we also had some other observations. We listed the pressure values here, and we just noted that the pressure is greater, or the pressure range is greater throughout the die for the 4,000 millimeter one than the other two. It's like as you increase the width and mass flow rate, it had an effect of increasing the range of the pressure. Although we did recall that the die in theory isn't actually flowing properly, the material's not being pressurized enough, so this is probably still too low for a practical, realistic die that you would use for manufacturing or something like that. So continuing on, we have the results. This is the pre-optimized dies, just the results that CompuPlast calculates and shows once you finish calculating the flow rate variation. So these all look like small charts. Most over them you can see like the big versions, but basically the ranges are what's most important here. We just wanted to see what the trends were, even though it might not be completely accurate because the die is not realistic. We saw that the flow across the velocity and the velocity across the die all increased in range, but there weren't really any solid trends for the other few, except for the residence time. The residence time increased, but the shear was kind of inconsistent between them. So we just thought it would be beneficial to list that, since it's what we observed. So the main conclusions that we just saw in the results section we'll go over in more detail in the document.